Welcome back, YouTube community. This is Prithvi Trinath. This week we'll be exploring fast Fourier transform, that is FFT. So this is the outline of the presentation. We'll start with the introduction to FFT. This will be followed by the extraction of respiratory signal from PPG signal using FFT and IFFT. This will be followed by computing the respiratory rate using again IFFT, followed by the analysis of the results. IFFT stands for inverse fast Fourier transform. FFD stands for fast Fourier transform. FFT is basically an algorithm that computes the DFT of a sequence or its inverse, and as the name suggests, it's fast. That means its computational complexity is quite low compared to DFT, and thus the speed is pretty high, very high. Uh, as you all know, Fourier analysis converts a signal from its original domain, maybe time, into representation in the frequency domain, or even vice versa. So we have two kinds of fast Fourier transforms. One is DIT-FFT and other one is DIF-FFT. DIT-FFT stands for decimation in time FFT, and DIF-FFT stands for decimation in frequency FFT. So this is the derivation for DIT-FFT. So we divide the given input signal into odd and even components, and here the derivation goes like this. We wouldn't be going much deeper into derivation as of now. So moving on. So this is the concept required for our experiment today. So first thing what we need to do is apply moving average filter to eliminate the high frequency noises. This would be followed by computing the DFT of the signal using the FFT algorithm in order to reduce our complexity and optimize our algorithm. This will be followed by removing the respiratory signal frequency components, then taking the inverse using FFT. This will result in clean PPG pulse. Similarly, removing the components of PPG from the spectrum and applying inverse will result in extracting the respiratory signal. So fine. This will be followed by computing the respiratory rate, for which we need to find the index k of the first peak in the magnitude response of PPG component removed respiratory signal spectrum. And for our information, the frequency range of a respiratory signal goes from 0.05 Hertz to 0.5 Hertz, and that of a PPG signal goes from 0.5 Hertz to 5 Hertz. So corresponding for a given index k, corresponding frequency can be computed using this following formula, where f is the frequency, k is the index, capital F is the Fs is the sampling frequency, and n is the length of the signal. So let's now jump into the Arduino code. So there is actually an inbuilt library for FFT provided by Arduino. We'll be using that library that is mentioned here. That would be of this form. In order to include it, you need to follow this syntax. Well, this is my class FFT, which I would be equating to the inbuilt Arduino FFT class. So X is my input. I have 750 samples, but in order to compute FFT, we need of radix 2. We need something to the something which is of the power 2, which is in the form of 2 power n. So 2 power n, which is closest to 750, is 1024. So our samples are 1024. Sampling frequency is 25 Hertz, and we have the signal for 30 seconds. So these are the various variables required. So let's get started. Initially, we are initializing everything to 0. This will be followed by applying moving average filter on the signal in order to remove the high frequency noises as told earlier, followed by mean removal. These are the pre-processing steps which are mandatory in order to remove unwanted noises. So now let's plot the input signal and even the smooth end signal. As you can see, blue signal is my input signal and red waveform is my smooth end waveform. As you can see, there is no much difference because the signal initially itself was pretty smooth. So, and since we have applied moving average filter of order 1, so there isn't much difference. They are almost the same. Since there wasn't much noise, We didn't smoothen it further because that would again change the shape of the signal. So fine, let's move on. This will be followed by computing FFT. So we would be using this command FFT dot compute, uh, and VReal, and the inputs here are VReal, that is my matrix which contains all my real components of samples, B imaginary, followed by the number of samples, and this FFT forward tells that it's FFT, no, and not inverse FFT. So, so you might be having a doubt regarding where the output will be stored. So output will also be stored in VReal and VImaginary. So this is just a matrix. You can name it anyway. I have named it VReal and VImaginary. So these are only my inputs. These would be overwritten with my outputs. So you need to be careful while giving these as inputs, because after this execution, you will not have the inputs in that. You will have the outputs. You'll have the magnitude spectrum in it. Uh, you'll you'll have the Fourier transform in it. Since I have the Fourier transform and I need the magnitude spectrum, I will be computing the magnitude spectrum here. So, and followed by, now what I'll be doing is I need the components of respiratory signal, and we know that the frequency of respiratory signal will not be higher than 0.5 hertz. So from this equation, solving this equation, I can get the value of k, which is here is about 21. So using that, uh, I'd be finding the peak between index 0 to 21, and I'd be eliminating that peak in order to get a clean PPG signal, and I'd be putting a window of say 5 or 7 and retain that peak and the window elements and remove the entire other things in order to extract the respiratory signal. That is what has been done here. So let us plot these things and see how they are. Upper one is the magnitude spectrum of PPG, clean PPG signal, and lower one is the magnitude spectrum of only respiratory signal. So moving on. So since now we have actually separated the two components, which is only respiratory signal spectrum and which is only clean signal, clean PPG signals spectrum, we'll be computing inverse DFT in order to get the signals back, in order to get the clean signals back in time domain. So what we will be doing is we will be using FFT reverse to compute inverse DFT. We have initially used FFT forward to compute DFT, and now we will be using FFT reverse to compute IDFT. So these are my inputs and the samples, as you all know, 2 per 1024. And after computing these things, we will be changing that from complex, since our results might be in complex, we will be converting those things from complex to what you say real, using this command fft.complex to magnitude. Here my inputs will be real part, imaginary part, and samples, and the final real magnitude will be stored in this real part, whatever be the variable that you give. So, so now we'll plot the input signal, respiratory signal, and the clean PPG signal. You can see the blue waveform is my input signal, which is PPG plus respiratory. Green signal is my PPG signal, and this red waveform is my respiratory signal. Thus, we have extracted both respiratory signal from a given PPG signal, and have also obtained a clean PPG signal from the given signal by subtracting it, by removing it. So now let's find the beats per minute of this respiratory signal using this one as 60 into fs into index by the number of samples. So cool. The beats per minute we have obtained is 18, nearly 18, which pretty much lies in this range. So, and the frequency is somewhere in between 0.05 and zero point 0.2. So, well, we have pretty much efficiently computed the respiratory rate from a given PPG signal, given noisy PPG signal. Kudos to us. So now let us implement the same thing on MATLAB also and check the results. So I have taken the same input. And let us run this code. This is the given signal. This is the Fourier transform of that signal, which we have computed using DFT. Since MATLAB uses my processor, and since my processor can handle the computations required for 750 samples, I have just used a simple DFT which I have written and not FFT. So, and this is the Fourier transform with respect to the frequency. So now what we need to do is, this is the index 21. So we need to uh, nullify all the values between 21 and 750 minus 21 in order to extract the respiratory signal in MATLAB. And we need to nullify everything between 0 to 21 and from 750 to 750 minus 21 in order to obtain the PPG signal. So we have done that here, and applying inverse DFT, we get this following signal, and the beats per minute here also are somewhere around 20. So thus we have verified even in MATLAB that what we have computed in Arduino was right. So cool. From given PPG signal, we have computed the respiratory rate. Kudos to you all for as you can now compute the respiratory rate from a given noisy PPG signal.